let's talk about binary. Binary is a numbering system that you've probably seen. It's made up of 2 digits, and only 2, 0 and 1. Normally we have a decimal system, which uses 10 digits, as you probably know as well. And this is called decimal. Decimal meaning deci for 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the question is, how do we get all the values that we can make with 10 of these digits and fit them into only 2 digits? Seems almost impossible, but it turns out to be very simple. All we have to do is, let's say we have a binary number 0001, for example, and let's put it in columns. This is the first step. Second step is to write some values to give each column a value. So we start at the top right and we write number 1. Then we go to the left and we double it every time. So 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. And you would continue if you had more columns, but I only have 4 columns. So some things to know before we calculate this value. Each one of these numbers underneath each column is called a binary digit. And for short, we keep the B and we keep the IT, and this becomes a bit. So each of these values is called a bit. Now let's calculate what these bits add up to. It's very simple. We start from the right and we check who is raising their hand. And by raising their hand, I mean who's a 1. So 1 is raising their hand, 0 means that they're not. So the guy in the first column, worth 1, is raising his hand, so we write his value down, right? We write his value from the column, or the row above his head. The guy at the 2 value is not raising his hand, so he gets a 0. The guy in the 4 value is not raising his hand, and the guy in the 8 value is not raising his hand. Add these up together. 1 plus 0 plus 0 plus 0, it's very simply 1. So 0001 is the same as saying 1 using the decimal system. Let's do another example. 0101. We do the same thing. Check who's raising their hand. The guy worth 1 is raising his hand. The bit worth 2 is not raising his hand. The bit worth 4 is raising his hand, so we write down 4. We write down his value because he's raising his hand. And the guy worth 8 is not. So we add these up and we get 5. So 0101 is the same as saying 5. Let's do one more. 0111. So we do the same thing. Who's raising their hands? Well, the guy in 1 is, and 2 is, and 4 is, but 8 is not. So we write down their values. 1 is, 2 is raising his hand, right? His bit is a 1. The 4 guy, his bit is also a 1, so we write that down. And the 8 guy is not, so we write 0. Add these up. 1 plus 2 is 3, plus 4 is 7. So 0111 is the same as saying 7 in decimal, or the normal numbering system. Now, in this case, we didn't really use this column, so you could omit it if you need to. If you only have leading zeros, then you can just shorten it. But we'll get more on why we might keep it a certain length later on. For now, you might be wondering, well, how do we write letters? Numbers seems pretty straightforward. What about letters? Because binary is really supposed to be able to encapsulate and encode any data. So the answer is pretty simple. There's an organization called ASCII, and I have written down what that stands for because I don't remember. It's called the American Standard Code for Information Interchange. And what they did is they listed out all the letters and symbols that we use often and just gave them arbitrary values. So A is the same, or is represented by the number 65. B is represented by the number 66. C is represented by 67, and onwards until Z is whatever, I guess 65 plus 25 is 90 maybe. So all we have to do if we want to write A is look up his number, and there's charts that have all these that you can find very easily. So we look up A, and his value is 65. So all we have to do is write 65 using this system. to write the letter A. Now, we're dealing with pretty low numbers here, and we're almost out of bits. So it seems that we're going to have to add more columns, but let's double check that. Let's turn on all the bits, and that's the phrase that you would be using here, the correct phrase. Raising their hand is just an example, and I think it illustrates it pretty well. But really you'd say, is this bit set? And by set, it just means is it 1? This bit is not set. This bit is set. This bit is set. This bit is not set. So which bits are set? Well, we have all of them. So the guy in 1 is set. The bit worth 2 is set. The bit worth 4 is set. And the bit worth 8 is set. We add them all up and we get 15. 1 plus 2 is 3, plus 4 is 7, plus 8 is 15. So if we turn on all these bits, then we get 15. Now 15 is unfortunately much, much lower than 65. So the question is, how do we reach 65? And the answer is we add more columns. So we've pretty much maxed out what we can do with 4 bits. So let's add another one. We times 2, that's 16. Times 2 again, 32. And times 2 one more time, we get 64. And since we're going for 65, right, which is what A is, we can see that 64 is pretty close to 65. And fortunately for us, we also have the number 1 over here. So you might think, well, we could just turn on the 64 bit, 0 out the rest, except for the 1 bit. So I'm just going to underline this in blue so that we can see what we're focusing on. And we do the same system. We add the 1, and then there's 0, 0, 0, 0, and then this guy's on. What is he worth? Well, he's worth 64, so we add him, and we add them up. We get 65. So this is the same as saying 65, or in our case, it could be A. Now, I think this sort of begs the question of, well, is it 65 or is it A? We kind of have to make up our mind. And the answer is, it's really both. It really depends on who you ask and what the purpose is of writing down the value. So binary is only numbers. It's always going to be, in this case, 65. There's no other value. The question is, whoever's reading it, what system are they using? Are they expecting numbers? If they are, they got a 65. If they're expecting letters, then they need to look this up in whatever system you're using. Hopefully it's ASCII. The whole world uses ASCII. But you really can make your number 65 represent whatever letter you want. It's really up to the person reading it. They need to know what system you're using. So if you don't tell them the system, then they may not know what this is. But the point is that this all adds up to 65, and you can make this mean whatever it is that you want in your system. So there's a couple other things to kind of, I think, talk about. So let's say we have the same columns that we had before, 4 columns worth 1, 2, 4, 8, which is always this way. Any number that we write in here, like 5, what we'd consider this is a 4-bit number. It's a 4-bit value, because even though there's a 0 here, we're using 4 bits to represent a number. And this is very important, and we'll go into an example as to why we need to know the bit length, or the bit width is what we'd call this. First, the bit all the way to the right is called the least significant bit. Make sure I spell that right. Or, let me put it in blue, LSB for short. Okay? And then the one all the way to the left, or the highest value that you have in all your columns, it may not be 4 columns, it may not be 4 bits, it could be 16-bit or 32-bit or 64-bit, like in modern computers. This one is called the most significant bit, or MSB. And this is important to know sometimes if you're reading a data sheet or something for some kind of hardware or components. It might tell you what it's expecting, and it will tell you whether it's referring to the most significant bit or the least. So it's just good to know that the MSB is the one that's worth the most in its column. on whatever, on the amount of bits that you're dealing with, and the one to the right, excuse me, is the least significant bit. Now let's talk about why it's so important to know your bit length. Let's say we're going to send a message to our friend, and we want it to be kind of like secret. So we're going to use binary, even though it's not so secret, I guess. But let's say we're going to send the values 1, let's say 2 and 3 to make it simple. So let's encode 1. We know that it's 0, 0, 0, 1. I'm going to run out of space here. 2 is 0, 0, 1, 0, right? Because we're only turning on the bit worth 2 to get 2. And then we just need to add 1 to this to get 3. So for 3, it's 0, 0, 1, 1, right? The 1 bit is turned on, the 2 bit is turned on, the rest are not, so 2 plus 1 is 3. So to send 1, 2, and 3, we're going to write 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. So the question here, when your friend sees this, they're going to say, well, what's the bit width, right? What's the bit length? Because if you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Somebody could argue that this is a 12-bit value. But you know that it's actually a 4-bit value. So what that means is every 4 bits you would start over. So in this case, we split it into 4. Or into 4 bits, I should say, which splits into 3 sections. So this is basically these columns. This is these columns again. And this is these columns again. So without knowing the bit width, you really have no idea how to determine when the columns sort of reset back to 1. So we have 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8, and that gives us the correct values. But if it was a 12-bit value, then we could simulate that too. We can say, well, 12 rows or columns is 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. How many is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1024 and 2048. So if this was a 12-bit value, it's a very different result, right? We could do it real quick. So we have the 2 first bits turned on, and we have 3 zeros up here, right? Is that still on camera? It's not. So we have 2 of the first ones, 0, 0, 0, 0, 0, 0, then we have a 1, then we have 0, 0, then we have 1, 0, 0, 0. So we need to add these all up. We have, looking at 256, his hand is raised, so 256 plus 32 plus 2 plus 1. So this is 256, doesn't look like it, but it is. So plus 32 is what, 288? Is it? I feel like I did this wrong. But 256 plus 32 is 288, plus 3 is 291. I'm not sure if I added that up right. But the point is that by looking at it as a 12-bit value, it's very different to the numbers 1, 2, and 3, which are these much smaller 4-bit values. And you could even cut this up into 3-bit values. So it is a bit ambiguous without knowing the bit width of what you're dealing with. And now it looks like weird aliens looking at me. But in this case of 3 bits, you're going to get totally different numbers too. And we can calculate that. I won't do it here, but you could do it. It's pretty easy. So 0, 0, 0, 1, 0, 0, 1, 0, 0, and 0, 1, 1. And it looks like, you know, what's this? These are 4s. And this is 3. So it's what, 0, 4, 4, 3. But I won't do the chart. You can do the chart if it helps. So the point is, seeing a string of binary numbers, you don't really know what the value is. You only have half of the puzzle. The other half is what the bit width is, or the bit length. And then one more thing, I feel like binary sometimes looks a little bit more cryptic than it is. Cryptic. For example, like who says, or why do we multiply by 2 here? Seems very strange, but it's actually quite similar to decimal, and we can do a quick example and show why. If we have a simple decimal number like 1, and we add 1 to this, so we get 2 and 3, so we're going down, right? And 4, we keep adding 1. Well, if we go low enough, or high enough, I should say, we're going to get to 9. Now, if we add 1 more to 9, then we know that it makes 10, but why does it make 10? And the answer is the 9 has no more digits to go up to. This is the last digit in the decimal system. So it actually resets back to 0. And then there's actually a carry that happens, right? To add the 1 to make 10. And if we continue doing this, then this becomes 11, 12, and it goes all the way to 19. And the same thing happens again. If we add 1 more to this, then the 9 has nowhere to go except resetting to 0. And then it adds a carry to the 1 to make 2. So we get 20. So this is how this works with decimal. And if we compare it to binary, it's the exact same thing. We just need to remember that instead of having 0 through 9, we only have 0 through 1. But all the rules still apply. So if we start at 0, and we could have started here at 0, right? And just added 1, and we get 1. So if we start at 0 and we add 1, then we get 1. And if we add 1 more, then in the decimal system, we can go to 3, we can go to 2 from 1. In this case, we don't have a 2. So it's treated like a 9. And it resets back to 0. And now we have a carry. So we get 10. 10, of course, in binary, if we use a 4-bit example, 1, 0 is 2. So we have 0, 1, 2. Well, let's keep going. We add 1 more. We have space here, so you always add it. In this case, I guess I didn't really explain that properly, but you're always adding it to the place where it can take the number, starting with the lowest value. And similar to binary, the lowest value in decimal is also on the right. So if we add 1 more to this, there's a space here to take 1. So this adds a 1, no need to carry, the 1 comes down, and we have 11. Well, 11 is of course 3. The 1 is turned on and the 2 is turned on, or we could say this guy's hand is raised, what's he worth? 1. This guy's hand is raised, what's he worth? 2. So this equals 3. We add them up. 1 plus 2. These are zeros. They're not included. And if we keep doing this, it's kind of fun, actually, to see how binary is built. It's very, very simple. It just looks very cryptic. So if we add another 1 to this, then we add the 1 here on the right, all the way to the right. Sorry, we added 1. We add the 1, and then we get 0, because there's nowhere else to go, right? There's no number 2 in the binary system. So he becomes a 0. We add the 1 to his other column, but this guy also has nowhere to go, so we get another 0. And then there's a carry, and it becomes a 1. So I'm going to rewrite it right here. I'm going to write 100. All right, we add 1 to this guy, he becomes a 0, which carries a 1 to this guy, which also becomes a 0. He resets. And then there's a carry, which becomes 100. And 100 is, of course, oops, I'm getting sloppy now, is 4, right? 0 is the 1 bit is off, the 2-bit is off, the 4-bit is on, and the 8-bit is off. So we get a 4. So this continues all the way. You would then, to get 5, of course, 100 just becomes 101, because this guy can take the 1 addition without adding any carries. To get 6, we add 1 to him, which carries over. So he becomes a 0, he carries. But the 0 can take the 1, so he doesn't have to carry to the next guy, so we get 110. Or really, we should read it as 110 in binary. The 2 is turned on, and the 4 is turned on. So that's 6. You may have noticed as well, if the 1 bit is not turned on, you can easily tell that it's an even number. So and odd numbers all have the 1 turned on. That's a quick little shortcut. And I think the sort of the way to look at this as well, if you want yet another example, let's say we have a number like 156 in decimal. It's very similar to binary. What do these columns represent? If we remember way back in grade school or elementary school or whatever we call it, this is a 1's column, and this is a 10's column, and this is the 100's column. And this is a very interesting pattern here, right? This is times 10, and this is also times 10. Now with binary, we know it's times 2, times 2, times 2. In decimal, times 10, times 10, times 10, and we can keep adding times 10. So it's, again, the exact same thing. The only difference here is decimal 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 10 digits. So what we call it is a base 10 number. That's just, I guess, a technical description. Binary has 2. So this is a base 2. So all we're doing here is using the value of the base of what the number is. In this case, we have 10 digits, so we use the number 10. In this case, we have 2 digits, so we use the number 2. And we start with 1, and we multiply by whatever number of digits we have available to use. In this case, we only have 2, so it's 1 times 2 times 2 times 2. And with 10, it's 10 times 10 times 10. So that's another way to look at it. One last thing, I'm going to get into negative numbers, but I think I should do it in another video because there's 2 systems to make negative numbers. One of them is very simple, but it's not used very often. And that simple system is if the person that's reading the numbers knows that you're going to be using negative numbers, then the column that's the most significant bit is not going to be a value anymore. It's just going to be used as a flag or as an indicator as to whether the rest of your number is negative or positive. So if we had the number 5, then you can mark it as negative by turning on the most significant bit. And this is only if you're using numbers that may be negative. And this, again, this is agreed upon by who's writing the numbers and who's reading them. If you know it's only positive numbers, then this can be an 8. This could be the 8 column. But if you know that there may be negatives, then you would use it to mark whether it's negative or positive. But I'm going to go deeper into negative values in the future. Just know that without considering this to be a negative number, we know it's 8 plus 4 plus 1, so 13. But if you are using negatives, then this would actually be negative 5. So it can get confusing, but I'll go into it deeper in another video. And this system here is kind of outdated, but this is where we should start with negative. So that will be the next one.